Thanks, Mike. Yeah, so my name's Josh. I'm a third year PhD student here at Cornell University. Got my ham license last summer and have been involved with the Ham Radio Club here for a couple of years now. So I mostly work on spacecraft. I'm part of a spacecraft lab here, small sats, CubeSats, even smaller things called chipsats that I'll get into for the bulk of this presentation. And yeah, it's been quite the radio journey trying to get these small chips heard in orbit, and I'll be talking about that challenge today. So for those of you unfamiliar, chipsats are essentially satellites on a chip. It's been developed at my lab as well as a couple others, though we're the only lab that have flown them in space at this point. And they're just small PCBs. They take advantage of smartphone type electronics. The original intent was for them to be more nanofabricated, but this is just so much easier to prototype. So it's got a solar cell, some basic sensors, a microcontroller, a radio, an antenna, and all. And it can essentially achieve what you'd expect from a basic functioning spacecraft, all of the essential subsystems. In no way does this achieve what you'd expect from a larger spacecraft, like an individual chipsat of a couple centimeters. Can't do as much science, but if they work in swarms, large constellations, they can do types of scientific missions that larger spacecraft never could. So my research involves the types of missions that can be possible. Previous PhD students looked at how to deploy these in kind of mothership CubeSat deployers that would release a ton of them, and then you could have them kind of talk to each other over shortwave radios and even talk to ground stations. Folks have also looked at their use as sort of a ground network for planetary exploration on the moon or other planetary bodies. And my personal research, more kind of academic side to get me out of here in 5 years, is looking at EDL. How could they survive if they re-enter from orbit? If they do fall through the atmosphere, how do they disperse? So those are some of my applications. There's one suborbital mission. It's not necessarily from orbit. You could just release them from high altitudes and have them spread over a wide area. So I've been doing a lot of that. This is actually a mission we're hoping to launch in a couple of years. And I'm currently trying to figure out how to listen to 100 chipsats at once, which is not the most straightforward thing for me, at least. One other interesting case of them kind of landing or even re-entering from orbit is this idea of just bypassing radio entirely. Maybe not a great topic to bring up at a radio conference here, but if you store all the data on an SD card and you're able to find that chip later, probably through radio or getting their last known GPS coordinates, then you can get a significantly larger amount of data that you wouldn't be able to transmit through radio communication alone. So that's just one other idea that we have for these things. There's a lot of kind of mission concepts for this. This is my main project that I'll talk about a little bit. It's pretty much been my life for the past 3 years at this point, and it's a CubeSat mission, a 1U CubeSat that's going to be deployed from the space station. And the CubeSat itself is a deployer. You can see that it's got a compartment with a door that opens, and when that happens, it releases this light sail into orbit. Light sails, for those of you who are unfamiliar, they sort of take advantage of photon pressure from the sun or from artificial light source, and depending on their mass to surface area, you can get pretty high accelerations and actually navigate in space. So on this light sail, I have these 2 chipsats here. There's 2 on the other side as well. So here's a close-up of the chipsat on the light sail, just a little CAD model here. And this allows the light sail to actually separate from the CubeSat. That's normally not the case. And going back to this comparison diagram here, you can see that Alpha on the right is a significantly smaller light sail than the few that have flown. Folks have started flying these things in 2010, and there's been a handful since. And typically they are much larger because they have to carry a pretty bulky spacecraft with them. But you can see from this little chart here, sort of my metric for performance is this mass to area ratio, and this bottom bar in gray. And Alpha is pretty comparable to the others that have flown so far. So we can accelerate. We won't in this case because of the free launch opportunity is from the space station. We're not going to be very high up. At best, we might only be in orbit for 2 days before this thing falls down due to atmospheric drag, but it's a good demonstration of the deployment and a good motivation for funders to one day fund a higher orbit launch for this spacecraft. And during those 2 days, to have the full demonstration, it's not just getting a picture of this thing ejecting, but we do hope to actually receive radio signals from these chipsets. I don't expect a lot of passes over Ithaca, and we're definitely looking for folks to help listen and track this object. Yes, that's a bit about Alpha. And like I said, if it's successful, it could go further places. We're working on steering through piezoelectric actuators. And if you can steer and you get high enough of an initial orbit, you could escape Earth's orbit. You could go to the moon. You could go to interplanetary trajectories. The radio problem for these is not solved yet. I'm still focusing on Earth orbit, and that's what I'm going to talk about once I get past this introductory material. So there's still a bit of a challenge to hear these things in low Earth orbit, let alone outside of that. And then futuristic, around 2050s or more, there's this concept called Breakthrough Starshot, and it's this billionaire-funded journey to send probes out to our nearest star system, Alpha Centauri. That's why my CubeSat's called Alpha. It's sort of inspired by this larger mission. And our chipsats here were sort of rebranded by that program as Star Chips, sort of this lightweight probe that would go in the center of these light cells. These are not actually solar powered. These are going to be propelled by laser light and accelerated to 20% of the speed of light. And there are a million problems regarding this mission, one of which is definitely radio communication that has not been solved yet. But they're targeting some sort of computer sensors, maybe even a camera to see aliens one day, that will weigh in total 1 gram. We're at around 2.5 grams for our prototypes at the moment. All right, so in terms of what's actually been accomplished with these, because it's nice to get dreamy, but still we're limited to the tech of today. So we made some prototypes in 2010. We put them on the space station that showed us that these types of commercial off-the-shelf electronics can survive in a harsh space environment for a couple of years. And we got them back, they still worked. They were facing on the far side, spaceward, so we didn't actually get radio signals from them at the time. But then we had a couple missions that deployed about 100 of these chipsats in low Earth orbit. And folks did hear these, but it, as of now, not a full decoder, and I'll get into that. Since then, we've done some impact testing to show that they could potentially crash on the moon or something, and we've done short ground-based applications with a newer generation that had a GPS chip as well as a few other sensors. And that was over distances of a kilometer or less. So KickSat was the only one that really demonstrated long-distance communication. And that was my model. Here's just a little animation. I bet it'll be a little laggy over the Zoom screen sharing, but hopefully this gives you a sense of how the chipsat's deployed. They're up there for, I think, a week or two before they deorbited. All right, so yeah, nice dreamy animation there. It was actually crowdfunded. So Kickstarter supporters are actually able to back and fund their own personal spacecraft, which is a cool kind of democratizing idea towards access to space. So, all right, getting into the technical side here. KickSat was possible through the work of that PhD student, Zach Manchester, and he had proved, at least in theory, that you could hear these 25, or actually in this case, 10 milliwatt transmitters that were based on the CC430 chip from TI, and hear it on the ground with just the equipment you see on the right, a handheld Yagi, some kind of low noise amplifier, and just an SDR on a laptop. And there's some pretty interesting math that he did to prove this. He used a technique called matched filtering, which essentially represented each 1 or 0 each bit that you transmit as this long string, the pseudo-random number. And you'd be transmitting essentially 64 bytes for every 1 byte that every 1 bit that you'd like to transmit. and you'd replicate the signal on the ground, the known signals that correspond to these ones or zero representations, and use this matched filter algorithm, sort of like a sliding dot product to get some kind of correlation. In reality, it did not work as well. As you could tell, these antennas are a lot bigger than the ones he proposed in his paper and tested with. So signals were detected. This is a radio telescope in Denmark. This is one, I think, on Stanford University's campus that he had access to. And they were able to detect signals. As you can see, there actually is a correlation. There's two dots on the top here that are the spikes representing to a 1 and 0. So they were able to detect signals from a few of these chipsets. But as you can see from this SDR screenshot here, it is very, very faint lines. And this happened in 2019, and no data was ever published from this mission. I don't think anyone actually decoded actual packets from it. So this brings us back to Alpha. When I joined Cornell, it was right around this time that mission was launching, and I was told it was a solved problem, that I can just reuse the same algorithms, the decoding algorithms that Zach had used on that mission. And the more deep I get into this project, the more I realize that none of these problems are actually solved. I have a long ways to go before this launches. We're getting close. The NASA launch providers are ready. And at this point, I'm really excited to report that the CubeSat is fully ready. That was a long saga as well. So all that's left now is getting the chipsats ready, and particularly this communications link. So my first attempt at doing this is sort of retrying what was done before. And it was a 2-year journey with a lot of learning for me, bugging a lot of people, including Hojo here. Picked up some good new radio, learned what IQ data meant. It wasn't a one-to-one correspondence with the previous TI chips. So those were, like I said, those were CC430s. Those use minimum shift keying. The new ones are CC1310s, different frequency, also Gaussian frequency shift keying. So I got to learn the difference between those, pick up a bit of hardware myself. This is a little launch pad that allows me to program the chipsat. And yeah, I got to learn what fast Fourier transforms were and IFFTs, and do this whole correlation algorithm in the frequency domain. Didn't work so well originally. You can see that there are a lot of correlations that don't quite correspond to what I had in that previous plot. We did get there eventually. I definitely made a lot of mistakes along the way. At first, I tried demodulating it first and then decoding it. Not the way to go. It really does have to happen at the highest level by replicating the signal and matching it at the frequency domain level with the raw IQ data from the SDR. So once we got there, we did a few balloon launches, and we actually got some decent data. You can see that there is a noticeable correlation representing a 1 and 0 on this, and we were actually able to get a full decoder out by detecting a 1 or 0 above the lines of 1, below the line is a 0. And yeah, we got some data, but nowhere near the distance we were hoping for. It was able to work at 20 kilometers max without any attenuation, and we need at least 400 kilometers to orbit. So either I'm doing something wrong or this tech isn't quite there. And given our experiences with that other mission that launched, I'm assuming that honestly just using frequency shift keying and using this matched filtering algorithm isn't quite enough. It also takes forever to actually decode these things. On an 8-core Mac, it still takes several minutes to decode a packet. So, oh yeah, as a tangent, we didn't only test the chipsats on here. We also got to do a really cool deployment of the light cell this past October. So I wanted to show a video of that. So there were some successes here. This was a great morale booster for the team. We triggered a deployment from our ground station for the CubeSat using CubeSat tech that I'll talk about in a second. And this is the light cell coming out with not a real chipsat on the side, but that's just a mock-up one for the purposes of some cool video. So some fun times there. And the particular radio that triggered that deployment is an Iridium modem. So I just want to quickly draw attention to this. Our main CubeSat deployer takes advantage of this tech so that we don't need some expensive equipment here at Cornell. We can just access our packets through email, and we actually export it onto this cool dashboard called Kibana. And then we can also send commands through the Rockblock API, and we created a user interface for that as well. So that's been a lot of fun. Obviously, too high power and too large for our chipsets. So my next solution, since I couldn't get the TI stuff to work very well, was to contribute my own chipset to the sequence of ones that we've made. And I've drawn from a few sources here. So primarily the change is LoRa. And I'm using these Hope RF modules. Originally the RFM95 for the 915. Now I'm kind of testing the RFM96 for the 433 frequency. And yeah, I love it for a lot of reasons. One, capability. In the balloon launches we've done so far at 915, it far outperforms the old chipsets and their ability. And I can actually decode these live. Takes about a second to decode something straight from an Arduino IDE, so it's super easy to use and great for some of the undergrads I work with to pick up pretty quickly. And then in terms of actually getting listeners, like I mentioned, our light sail, our chipsets might only be up in space for a couple of days once it launches. So sure, I can email all of you and find more hams around the world to listen in, but there are really cool networks out there for LoRa now, such as the TinyGS network that can be tuned to listen and decode our packets for us. So that's a huge help. And I bought a bunch of these ESP32 modules that the TinyGS folks recommend, and they've been working great. So we're not the first chipsat to use LoRa. Just as a disclaimer, there is this other group called Ambisat, and you might notice this animation is very similar to the one I showed. So, you know, they copied us, we're copying them a little bit. It's all open source. And they have not flown yet. So they've developed the tech and they're selling kits to a bunch of folks. And they still have some communications problems and even just PCB problems to work out before they're ready to fly and get a launch opportunity. So we're definitely going to fly first. And I'm sort of drawing from both the Ambisat tech as well as from the previous chipsets we've designed here at Cornell to make the new design. We've made a prototype so far. You can tell this one does not have an antenna on it. So the actual PCB is going to be ordered probably by the end of this weekend. I'm doing a final review now. And at least we've made a prototype. We've learned a lot of SMD soldering in-house. We got a reflow oven. We've learned stenciling. So we've gotten pretty good at soldering really tiny things now. And making a prototype for $40 and getting it wrong is a lot better financially than sending it out to a board house and then realizing the same mistake. So we've learned a lot from these, and we're able to program them, and this new PCB sort of incorporates all the lessons learned from that first prototype. At the time of the balloon launch opportunities with Hojo and the Ham Radio Club, we weren't quite ready to fly this chipsat prototype. So we ended up using that same Hope RF module on these Adafruit Feather boards that cost about 35 bucks. And we just soldered a wire antenna onto this. And those performed very, very well. So with an attenuator on board or in line with the receiver, we were able to simulate roughly over 200 kilometers of distance, which is still not enough to get to orbit. So I'm looking to change to 433 just to get that extra distance. And that's sort of the goal of this weekend's launch. I'm going to launch a payload with two of these Adafruit Feathers, one 433 and one 915. And just get some data about how much better it performs. Like theoretically, it should be double, but I do want to verify that myself. And yeah, this is the final slide. So in terms of switching to that frequency, which I think we're going to do, I'm looking at antenna ideas. 433 antenna is definitely larger. It does fit on our light sail, but I don't know if a PCB helical antenna is really the way to go. Certainly a little more directional than say a monopole antenna. So I'm personally looking for advice. I'm looking for something that's small, lightweight, compact, that can fit on a PCB. If it protrudes out, we're thinking some kind of shape memory alloy wire like nitinol. We've used that in the past, so we could maybe attach a dipole or a monopole to this. Ideally, something that's not so directional. We don't have a lot of pointing control in our lead cell, so the less directional, the better. And yeah, that's it for me. Definitely want to thank a bunch of folks here at Cornell, our technical mentors, fellow lab mates, and definitely our organizations for our launch opportunity and for funding my work on this project. And finally, all of my students. I manage a pretty large team here at Cornell, and definitely don't have any personal boundaries. They want to meet at midnight to 7 a.m. Doesn't matter. But I'm honestly excited to work with such a motivated group of students here. So we've done a lot in a very short amount of time, and hopefully we can get this done in time for launch. So yeah, finally, if there's time for discussion, we'd definitely appreciate any questions, some advice on those antennas, and if you have any longer follow-ups, here's my email address. Thanks.
Josh, I have a question.
Sure.
This is Phil, K9Q. I may have missed this. You may have said this, but what was the power level of that 512 PN method that you were using early on?
Yeah, so the original ones use 10 milliwatts. The newer ones use 25. And then the low raw, as you might know, can go anywhere from 25 up to, I think, 100 milliwatts.
Okay. And you said there was it was a 512, 511-bit PN sequence.
Yeah.
Okay. But there was no forward error correction?
No, that's built in as well. That's more to if multiple chipsets are transmitting at the same time, then the correlation algorithm doesn't work quite as well. So it's good to have that.
Okay, you know, I was wondering, I mean, what was the reason? Who designed this system? What was the reason for using the chips, the pseudorandom sequence?
I believe he was inspired by how GPS modules work.
Well, I mean, what was the purpose? Was it to deal with interference between multiple transmitters on the same frequency?
No, it's mostly just to get additional gain. The idea was that
the thing is, it doesn't do that, right? I mean, the power gain, if you refer to every data bit that you send, chipping like that does not provide any gain. It's wash. Only forward error correction will help that. What the chipping does is resist interference. It's really a form of direct spread spectrum.
Okay.
It spreads the signal to a wider bandwidth. And so it looks weaker, but when you collapse it down, it's just like it was never spread in the first place. Only forward error correction will help you with power.
Gotcha. Okay.
Okay, I think that's maybe the reason why you were having problems with that system.
Okay, that could be why then. Yeah.
We can take this offline. I'd be happy to give you some advice. I mean, I worked for Qualcomm for 20 years, and so we know spread spectrum pretty well.
Sure. All right. Yeah, would really appreciate that.
Sure.
Any other questions?
Josh, there was one in the chat here. Someone suggested, could you use the sail material as part of your antenna?
We are thinking about it. So we have two 19-hole wires as a sort of a cross section for the frame, or cross section for the sail, and it might work for one of the chipsets. We're hoping to have multiple on there for redundancy purposes. So I'd have to think that through. Yeah, it's certainly a possibility. I see a couple other questions in the chat. So in terms of communications theory and just RF resources, we got Mike from the Ham Radio Club and a few other mentors who are kind of makers. So they invent toys over in Silicon Valley and stuff, children's toys. They have a bit of an RF background, but nothing too strong. So yeah, we could definitely use more advice if anyone's willing to stay in touch with the team. That'd be great. Yeah, if that's it, I'll turn it back to Mike. Again, for follow-ups, if anyone's got advice on those antennas, that'd be awesome. I'm about to do a deep dive into impedance matching circuits this summer, and I learned how to use a network analyzer. So I'm gonna have some fun there. But I have a feeling I'm gonna run into some trouble with this. So if anyone has some good solutions, definitely shoot me an email.